Alright, so in this final lecture capture video, we'll be discussing the law of multiple proportion. This law was based off of John Dalton's atomic theory of atoms, such as, for example, that atoms are individually indivisible, small, and you can have atoms of elements of different types because they have different number of protons, but of course, don't forget they also have the same number of neutrons, maybe some isotopes. So in his third postulate, he states the following, that when two elements form a series of compounds, the ratio of the masses of the second element that combines with a fixed mass of the first element can only be reduced to small whole integer numbers. So here's fixed mass, for example, 1. Okay, 1 gram of the other element. By fixing it, you don't have to worry about the other element. Now, for these type of series, like I said, they're for two elements when they form a series, though, of a compound. This is the only way it works out. So, if you've seen already that there are some examples in the book, or at least in lecture handle notes. In lecture handle notes, it does say this: that you can have element that contains both nitrogen and oxygen. So, what type of compounds can I form? Well, one, for example, can be NO. One can be NO2, or N2O, or N2O5. So notice here we have a series of compounds, and what they all have in common is the same type of elements, nitrogen and oxygen. But what's different about them is the ratios. For example, in nitrogen monoxide, the ratio is 1:1. In nitrogen dioxide, it's 1:2. In dinitrogen monoxide, it's 2:1. And in dinitrogen pentaoxide, its ratio is 2:5. Okay, so by trying to show and proof of Dalton's law's third postulates here, the law of multiple proportion, is you gotta do everything again by careful weighing. That's one part. So it kind of piggybacks on the law of conservation of matter, one, and of course the law of definite proportion. So for this example here, let's look at the following. Okay. So out here real fast. Let's come and illustrate this point exactly. Here. Alright, so let's erase this. So it says there two different compounds are formed by the elements carbon and oxygen. Okay, so we're looking at a series of elements that contains the element carbon and oxygen. Okay. The first compound contains 42.9% by mass and 57.1% by mass of oxygen. Okay, so in, let's say, compound 1, okay, what we have is 42.9% by mass carbon, and you have 57.1% by oxygen. Okay. Now, if you add these two guys up, the total percent will be equal to 100%. That is illustrating the law of definite proportions. Kind of. This is not experimental data, though. But the total should be equal to 100. Okay. That's what the total is here. But it says kind of, not quite. But we'll get there. All right. In compound number 2, what we have is that the second compound contains 27.3% by mass of carbon and 72.7% by oxygen. Okay, so these are two compounds. What they have in common is carbon and oxygen. Just the percentages are different. Okay, again, that is kind of trying to illustrate this idea of the law of definite proportion. Just by careful weighing, okay, than what you saw before, okay. But we're going to illustrate how this relates to the law of multiple proportion, okay. So what do we do first? Let's calculate first of all how many grams of carbon and oxygen we have in compounds 1, and also how much grams of carbon and grams of oxygen we have in compound 2. Now the way we do that is this. If you notice here, these are percentages, and if you remember, a percentage is nothing but a part over the total times 100 100. Now, if we assume, which we could do that, if we assume that the total amount is 100 grams of this compound, then we have the following then. That the total is 100 downstairs here. You multiply by 100 upstairs, so what do we get? That the percentage must be equal to the parts. Okay, so if this becomes 100, then 100 cancels out, the percentage must be equal to parts. So therefore I say the following. That if I have 42.9% of carbon, I must have 42.9 grams of carbon. Okay? Same over here. If I have 57.1% of oxygen, therefore I must have 57.1 grams of oxygen. Okay? So that's compound 1. Let's do the same thing in compound 2. Again, we assume that we have 100 grams of whatever this compound is. It contains the elements carbon and oxygen. But here, if we do that, then therefore we say if I have 27.3% of carbon, I must have, therefore, 27.3 grams of the carbon. Okay? And 72.7% of oxygen must mean 72.7 grams of oxygen. But the total is equal to 100. There you go. That's our assumption, and it works. Almost all the time you can make this assumption, which later on it will show up, especially when we start calculating both molecular formula and empirical formulas based on compounds percent masses that's given. So get used to this idea here of assuming 100 grams for the total to get the parts equal to the percentage. All right, so now next, what do we do here? Well, now that we have this information, okay, what we do is this. We're going to set up a ratio first, okay? So if you remember from the actual explanation behind the law of conservation, law of multiple portions, well, the next thing we got to do is this, is that we have to actually fix one of these elements, okay? So to make it just 1 gram, okay? So in this case, what we're going to do is this. We're going to take the mass of the oxygen, which is 57.1 grams of oxygen, divided by the mass of carbon, 42.9 grams of carbon. Okay. Remember, the second element in that series will be equal to 1 gram. So how does that work out? Well, if I take this ratio here, notice that my units do not cancel out. That's important. But when I reduce this thing, what I end up getting is the following. It is 1.33 grams of oxygen per 1 gram of carbon. There it is. So that's how many grams of oxygen I have in 1 gram of carbon. So therefore we have fixed this element. This will not change. Therefore, whatever is in this compound, the carbon only contains 1 carbon atom. But we don't know what's going to happen for oxygen. We repeat the same process for compound 2. Okay, so we come over here. We see that we have 72.7 grams of oxygen to the ratio divided by the amount of carbon. Because again, we're going to keep carbon as 1 gram, so we're going to fix it. Keep it constant. 1 gram of carbon. When you calculate this ratio ends up being 2.66 grams of oxygen per 1 gram of carbon. Remember the word per, like I mentioned before, means 1. So now we've fixed both carbons here. I mean, this guy, compound 1 contains 1 carbon atom. Compound 2 also contains 1 carbon atom. What we don't know yet is the oxygen. And this will help lead us to how to figure out what the compounds is for compound 1 and 2 are, referring to carbon. I only have 1 type, but then oxygen may vary. Okay, so that's the first part of the law of multiple portion. To finish it up, though, this is the next part we got to do next. So here we go. So we do this. We're going to actually take another ratio. But this time, I'm going to do this. We're going to take the ratio of compound 2 divided by the ratio from compound 1. I always tell my students to always take the big number first, up to the numerator, divided by the small number downstairs in the denominator. Because if you flip it, if you get the other way, where the big number is downstairs, the overall result will become a very small value. So what we're trying to achieve here are whole integer numbers. If you remember, anytime you're given a formula, water, H2O, you never heard it as, say, H1.5O. Okay, fractions don't work here. They have to be whole numbers here, whole values. 1, 2, 3, 4, 5, so on and so forth. So if you happen to get a fraction, let's say 1.5, okay, which is 3.5, really. So yeah, 1.5, which is 3.5. Okay, well if I take 1.5 and I multiply it by some factor, like say 2, I get 3. That's a whole number. You cannot leave it as 1.5. There is something as 1.5 of an element of that atom. You either get all of it or there's nothing at all. So whole number. So big number upstairs. So what I have, compound 2, which is 2.66 units, grams of oxygen. And I'm gonna stretch it out this way. I always do it for this type of problem. I'm gonna do a big. It's a ratio. It's a dividing. Got this over this guy. But I'm doing it on for a reason. So if you kind of bear with me here, let's check out these units. 1 grams, so it's 2.66 grams of oxygen in compound 2 divided by 1 gram of carbon. There it is. Now, if I divide it by compound 1, so what's the ratio there? What we have is 1.33 grams of oxygen. But here's the thing though, it'll be per 1 gram of carbon. So what I do here is this, since this number, this guy is already in the denominator, which has a denominator, and the number downstairs here, this guy, this 1 gram of carbon, comes upstairs in the numerator. So you bring it upstairs. So it's 1 gram of carbon. Just that way it looks nice and neat, just seeing the one single numerator and the one denominator. So again, it's per carbon. Like I said, it looks something like this, but it looks kind of weird seeing like that. But since this is already downstairs in the denominator, you get to flip it upstairs, then it becomes the numerator. Okay? So that's what we get here. Okay. Alright, so hopefully we got this part now. Now let's see here. What happens? What cancels out? Well, let's see here. Ready? So 1 gram of carbon, and the units cancel out with the 1 gram of carbon, so that's gone. Okay. We also have grams of oxygen. So that's gone. So the only thing we have here now are just some values, numbers. Okay. So it's just 2.66 divided by 1.33. Now, when we put in a calculator, the answer ends up being 2. So what does this mean exactly? Well, this is what it's telling me right now, is that in compound 2, okay, we just got over here, that there is twice the amount of oxygen present in compound 2 than there was in compound 1. Okay? In fact, I could do another ratio just like this between compound 1 to compound 1. But if I divide 1.33 divided by itself, I get what? 1. So the ratio here, the way we represent it, okay, the ratio is 2 to 1. So this is compound, the way we have it written is 2 to compound 1. That's your ratio. So going back to this, so now that I have this information, well, what do we do with the carbon? Well, we fixed it, right? Therefore, in all these cases, the amount of carbon present in either compound 1 and 2 have to be the same. That's just 1. So I know right away that the formula for compound 1 contains carbon, just 1. And in compound 2, there are also just 1 carbon. Now, the oxygen, though, based on this derivation right here, what's telling me is there's twice the amount of oxygen present, 2 times the amount of oxygen present in compound 2 than there is in compound 1. So therefore, in compound 1, the element ratio is 1 to 1. That's CO. That's called carbon monoxide. But in compound 2, though, since it's twice the amount than that is in compound 1, this one's formula, the ratio is 2. So that's CO2. That is carbon dioxide. Notice again, it does illustrate the law of multiple proportion that John Dalton predicted could happen. What happened? It's all by careful weighing here. And it's by masses. And come up with these ratios. So the first part is this. Just come up with the ratio of the element you want to fix. Normally in a problem like this, you're kind of told which element you want to fix. Okay? So that's one thing. So that should go downstairs in the denominator. That way at the end, the ratio becomes 1. It shows here. Then at the end, at the middle part, next part is you guys have another ratio between two different compounds. So I can have a third compound 3, same idea. Okay, so you can do it with 1, 2, and 3. That's the example I believe that's in nitrogen notes when it comes to the element that contains nitrogen and oxygen. So see that for more examples of other types. But they'll do this. The only thing is this though, this will not work though. The law of multiplication will not work though if you have more than say one extra element. So for example, hydrogen, carbon, and oxygen. Having 3 makes the problem a little more mathematically challenging, but it could be done. But it will not work, for example, if you have compounds that have different types. For example, carbon and oxygen, carbon, chlorine. You can't compare the two. Okay? So they have the same, at least 2 types of elements, good enough for us here. And in fact, something like this is what you will be doing in Chemistry 110. So Gen Chem Part 1. You actually do this in the lab to illustrate and prove that law of multiplication does work. And remember, it's a law. That means no matter what happens here, it should always happen over and over based on what happens in nature, based on this observation. It happens all the time. So you will illustrate this point again. That's why it's important to know, understand this now, but then apply it when you guys are ready to take Gen Chem Part 1. Okay. So with all that said, that completes this lecture capture video. And of course, we'll come back for another one.